Welcome to your Chapter 2 review for your Unit 1 exam. Again, I'm just going to our Dr. Higgs section. Remember, in here, I give you tips, and I have your Unit 1 exam review. Remember, I'm going to add some videos to it. These videos that we're making will eventually be posted to this Unit 1 exam review. And if you're wondering, where am I getting the PowerPoints from these review videos, it's all here. 1, 2, and 3. These are the PowerPoints I'm using in these reviews. So for this Chapter 2 review, I'm using this Chapter 2 lecture PowerPoint. These are just lecture PowerPoints I would have been using if we were still face-to-face. It's still from MASH, so it's still covering same material as our lecture PowerPoints provided by the department. I just use these because they're what I have and what I'm familiar with. But it's still, again, the same material. And again, not all of this in detail, it's just a review for providing highlights. So in this chapter, we're basically beginning our journey through that structural hierarchy. If you notice, in Chapter 2, we start off with our simplest level, chemistry, our chemical level. Chapter 3, we bump up to the cellular level. Chapter 4, we bump up to tissue level. We're just following our structural organization. So we have to do chemistry because at our base, our simplest level, we are chemicals. All right. And so, just like usual, this one is going to be some definitions. Now we're going to get into some more concepts and ideas as well. And when we talk about our chemical level, you might remember it's you being atoms and elements. So you got those definitions. What is an atom? And what is an element? Keep it as simple as in your lecture PowerPoints. For example, atom is the smallest unit of matter that retains original properties. Each element in your body, carbon, oxygen, hydrogen, they have their own unique properties, their own unique characteristics. And these unique properties are your atoms. And you need to know the parts to an atom. We call them the subatomic particles. 3 of them. It's protons, neutrons, and electrons. You got to know what charge do they have. Protons have a positive charge. Neutrons are neutral. They have no charge. And electrons are negatively charged. You got to know where to find them in the atom. Protons and neutrons are in what we call the nucleus, kind of like the core of the atom. While electrons are located in electron shells. And you need to know how much they weigh. And you got to think, this is an atom. This is super tiny. We cannot use normal units of measurement for weight. A pound is too heavy. A gram, a milligram, a micrograms are too heavy. We actually have to come up with our own unique units of measurement. They're called the atomic mass unit, or AMU, as an abbreviation. A proton weighs 1 AMU. A neutron weighs 1 AMU. An electron, believe it or not, is practically weightless. It has a 0 AMU weight. Okay, so now that protons are positive, they're located in the neutron, and they weigh 1 AMU, 1 atomic mass unit. Neutrons are neutral, they have no charge. They're also found in the nucleus of the atom, and they also weigh 1 AMU, atomic mass unit. And an electron has a negative charge. It's found in what we call electron shells around the nucleus, and they have a weight of 0 AMU. And when it comes to these electrons and their electron shells, there's even a certain number of electrons that could exist in each shell. Turns out these shells exist in multiple layers. We call them shells around the nucleus. The first layer is what we call the first shell, and going further away, you increase the number. So right around the nucleus will be move further out is the second shell, further out is the third shell, and you could keep going. There are more shells, but to keep things simple in this class, do not go past the third shell. We will not see any atoms or elements that go have electrons going past the third shell. And you gotta know how many electrons are in each shell. It's all on one slide. First shell only holds 2 electrons. You can kind of think it's not that much space. It's the inner layer. So it's only having practically enough space for 2 electrons. Move further out, you get a bigger circle. So you can imagine there's more room here. So hold more electrons. You could hold up to 8 electrons. And the third shell could hold up to 18 electrons. How questions look? I could say you have atom like sodium, and I can make up numbers. I don't have to use the actual true electron numbers. I could say sodium has 10 electrons. If sodium has 10 electrons, how many electrons are in the third shell? Let's go through it. If it has 10 electrons, well, 2 of them are in the first shell. That's already 2 of 10. Then the second shell could hold up to 8, so we'll fill it up with 8. Turns out 8 plus 2 is already 10. There will be 0 electrons in the third shell. Okay. Or one more example. I could say chlorine has 15 electrons. If chlorine has 15 electrons, how many electrons are in the third shell? Just fill them up. First shell will have 2 electrons, so that's 2 of our 15. Our second shell will have 8, so 8 plus 2, that's 10. And I'm left with 5. 5 electrons are in the third shell if it has 15 electrons. Okay, just know these numbers. First shell has 2 electrons. Second shell has 8. And the third 18. And notice they're all even numbers. Why? Turns out electrons love to exist as pairs. Why? If they don't exist pairs, you get some instability. It becomes unstable. Electrons love to have a pair. And if they don't, they will try to find the pair. And one way they could do that is by forming a bond. Alright. Well, still on that there. Then there's an element. You gotta know that definition too. An element is just a substance that cannot be broken down by normal, ordinary chemical means. If I were to pour an acid on oxygen, I cannot break oxygen down. Acids are like normal chemical means. Okay, just know the definition. Remember, this class is mainly memorization. Then we gotta know some other features. You gotta know some numbers now. Each element in your periodic table of elements has some unique numbers and some unique features. You gotta know these numbers. All right. Well, first one is called your atomic number. Usually the number above the symbol for that element. You gotta know what is the atomic number. And the atomic number is simply the number of protons. That is it. Okay, so I could literally give you a question where I say carbon has 6 protons. What is the atomic number of carbon if it has 6 protons? Well, 6. Because the atomic number is literally the number of protons. There's no calculation you need to do. It is a straight up number. All right. Keep going. We got to know some other numbers. You got to know something called a mass number. This one is a calculation, but still pretty short. The number of protons plus the number of neutrons, the mass number. So I can ask you to calculate a mass number on your exam. I could say carbon has 6 protons, 6 electrons, and 7 neutrons. If carbon has 6 protons, 6 electrons, and 7 neutrons, what is that carbon's mass number? Well, it's 6 protons. We know there are 7 neutrons. So 6 plus 7 is 13. Okay. Yep, I threw an electron number knowing you didn't need it. So I could throw in extra numbers like electron number. You just got to remember to ignore it because it's not in the formula. Remember, trust this class is very straightforward. Or I could work backwards. I could give you a mass number and ask you to come up with the atomic number or the proton number. Or I ask you to come up with the neutron number. How? I could give another example. I could say oxygen has a mass number of 20. If oxygen has a mass number of 20 and 8 neutrons, how many protons are there? Well, you got to work backwards. 20 minus 8 is 12. It has 12 protons. Or I could say it this way. If oxygen has a mass number of 20 and 8 neutrons, what is the atomic number? I can remember that's just the number of protons, so it's still 12. All right. So make sure you know atomic numbers, number of protons, mass numbers, protons plus neutrons, and be able to calculate it. And then we're not going to study all the elements on the periodic table. We focus on human anatomy. So we focus on the elements that make up your body. You have to know the 4 major elements that make up your body. It's hydrogen, oxygen, carbon, and nitrogen to memorize it. There are other elements in your body, but if you think about it, the majority of you is these four. About 96% of your body are these four elements over and over again, with a couple more sprinkled in. But know the four major ones. Just memorize it. Then again, back to definitions. You got to know what is an isotope. An isotope is an element where you vary the number of neutrons. That is it. Everything is the same except for the number of neutrons. That is it. That's what you see here. Hydrogen, normally, if you look at periodic table, it has an atomic number of 1, so it has 1 proton. And when you're stable without a charge, it's because the number of protons is equal to the number of electrons. So normally, hydrogen has 1 proton and 1 electron. But if you were to look at its mass number, turns out the mass number for hydrogen is also 1. So how do you get a mass number of 1 and an atomic number of 1? How many neutrons does it have? 0, normally. That's what you're seeing here. This one up top is representing the mass number. They have it backwards. Usually the mass number is down below and the atomic number is up top, but they flipped it for this example. So this one up top is mass number. 1 down below is atomic number. That's normal hydrogen. But I can make an isotope where I change the number of neutrons. And remember, if you change the number of neutrons, it's going to affect our mass number calculation. So if we were to add a neutron, giving them 1 total, because it originally had none, well, that'll change your mass number to 2. And you will have the isotope called deuterium. Or if I gave it 2 neutrons, that will change the mass number to 3, and you will get the isotope called tritium. Isotopes are just variations of an atom or an element where you really just vary the number of neutrons, which will affect the mass number. That is not the definition. Keep it simple. Definition is just the variation of an atom or an element where you vary the number of neutrons. And then this brings up something called radioisotopes. A lot of your radioisotopes are just plain old unstable isotopes. When you vary the number of neutrons, it makes some isotopes unstable, meaning they're going to vibrate, they're going to shake. And when they vibrate, kind of break pieces of themselves off. Protons, those extra neutrons, maybe electrons. And they will decay. When you break pieces of yourself off, it's like you're decaying. We call it radioactive decay. You might know this simply as radioactivity. You're just being around unstable isotopes, and that's bad. You don't want to be around radioactive material. Why? You're not going to become a superhero. You're not going to get special powers. When you're around radioactive material, you're really getting hit with all those pieces of that atom or element as they're shaking violently. And when those pieces hit you, it damages your cells, mainly your DNA. And that will lead things like cancer, not superpowers. Okay. Know your definitions. Then we begin to combine atoms and elements together, mix them together. We form mixtures. You can know your 3 major mixtures and what it takes to be that mixture. You got to know what is a suspension, what is a colloid, what is a solution. I'm going to give you answers, definitions, keep it simple. And we're mixing things together. And you can mix multiple things together. But to keep these examples simple, I'm just going to say mixing 2 things together. But you can mix more than 2. Okay. So in a suspension, let's say we mix 2 things together. In a suspension, when you mix 2 things together, one thing will settle to the bottom. When we say settle out, that means settle to the bottom. That is a suspension. Kind of thing going to the beach, getting some sand and some water in a bottle and shaking it up. When you put the bottle down, eventually all the heavier sand settles to the bottom and the water stays on top. That is a suspension. An example in your body is your blood. If you were to see blood sitting out, eventually all the red blood cells settle to the bottom. When you mix 2 things together and one thing settles to the bottom, that is a suspension. Then there's a colloid. And add 2 things to keep it simple. A colloid, when you add 2 things together, nothing settles to the bottom and nothing gets disturbed. You see both parts throughout the mixture. That is a colloid. When you combine 2 things together and they all stay throughout the mixture, nothing dissolves, nothing settles to the bottom, that is a colloid. Imagine having any gel or cream with microbeads in it. When it's in the bottle, do the microbeads dissolve the gel? No. Do the microbeads settle to the bottom of in your container? No. You see the gel and the microbeads in your soap and your gel and your toothpaste throughout the mixture. That is a colloid. And then last one is a solution. Again, keep it simple, adding two things together. In a solution, when you add two things together, one thing will dissolve the other. That is a solution. Think salt and water. Mix salt and water together. The water will dissolve the salt. That is a solution. Did the salt disappear? No. How do you know? When you taste it, it still tastes salty. It's just that it got dissolved by the water. So you have a watery solution. And in this class, we name everything. Anatomy, we name everything. You even got to know what we call the thing that does the dissolving and what we call the thing that gets dissolved. The thing that does the dissolving is called a solvent, and the thing that gets dissolved is the solute. Know that. The thing that does the dissolving, solvent, and the thing that gets dissolved, solute. Turns out water is a very powerful solvent because water could dissolve a lot of things. Solutes like salt or sugar get dissolved. So when you're making your lemonade or your iced tea or just plain old tea and you put your sugar in it, your sugar is the solute and it got dissolved by the water, the solvent. So just keep it that simple. Know these three mixtures and what's happening. Did you combine stuff and one settled to the bottom? Suspension. Did you combine and you see them both throughout the mixture? Nothing dissolved, nothing settled to the bottom. Did you combine more things together and one part dissolved the other? The solve dissolved you. You have a solution. Keep it this simple. All right, this class is very short because it's a lot of information. We know this class is a lot of information, so this is usually a straightforward class. It feels overwhelming when you fall behind and you don't keep up with the material. Okay. And you're able to make mixtures because really it's atoms and elements binding to each other. And you got to know how. They're binding to each other thanks to electrons in the outermost electron shell. Remember, electrons exist in shells around the nucleus. And it's electrons in the outermost shell that are helping to form the bonds. We call the outermost shell the valence shell. And the electrons in the valence shell are called valence electrons. They're what are forming chemical bonds. Like what you see here. If I want two hydrogens to stick together, it's thanks to the electrons in the outermost shell. All right. And then back to definitions. You gotta know what we call things once atoms and elements come together. I'm talking about a molecule and a compound. I know these definitions. A molecule is when you have two or more of the same element bound together. Like with this hydrogen molecule, I have two of the same atoms together or elements together. There's a molecule. Like a oxygen molecule. I bind one oxygen to another oxygen. I have a molecule of oxygen, oxygen molecule. Two or more of the same element. But I can have different elements bound together. I have two or more different elements, like methane. That's what you see here. Methane is one carbon and four hydrogens. Carbon and hydrogen is not the same. They are different. If I have two or more different elements together, that is a compound. Just know those definitions. All right. Now we're talking about bonds. You have to know your three major bonds. There are ionic bonds, covalent bonds, and hydrogen bonds. Those are your three major bonds. You have to know them in order from weakest to strongest, or backwards, from strongest to weakest. The order from strongest to weakest, the strongest are your covalent bonds. In the middle in terms of strength are your ionic bonds. And the weakest of all are your hydrogen bonds. That's the order. Covalent bonds are the strongest, ionic bonds are in the middle, and hydrogen bonds are the weakest bonds of all. And then you gotta know what it takes to form that bond. What's going on? So let's go through them one by one. We're actually going to start off with the ionic bond, the one that's in the middle in terms of strength. What's going on? How do you form this bond? What's the definition of an ionic bond? Know the first bullet point. An ionic bond involves the transfer of electrons from a metal-based atom to a non-metal-based atom, resulting in a salt. That is the definition. An ionic bond involves the transfer of an electron or electrons from a metal to a non, resulting in a salt. Like the salt you eat on your food is actually sodium chloride. This is the result of an ionic bond. How? Well, in sodium chloride, you have sodium and you have actually chlorine. Sodium is a metal, all right, and chlorine is a non-metal. And when you bring them together, they both have an unpaired electron. Remember, electrons love to exist as pairs. And so it's going to be these valence shell electrons that are going to try to bind together. How? The sodium, the metal, will literally give or transfer its electron to chlorine. And because it did that, it's not going to walk away. It's going to stay close. Why? Because a part of itself is still technically there. It just happened to give it to something else. This is an ionic bond. And at the end of it, you have your table salt. So again, an ionic bond is the middle in terms of strength, and it's the transfer of electrons from a metal to a non-metal, resulting in a salt. Keep it that simple. Right. And when you move electrons, remember electrons have a negative charge. If I lose my electrons, I'm losing that negative charge, so I'm actually going to become positive. We call these charged atoms ions. If I'm positively charged because I lost electrons, you could call me a cation. Or if I gained electrons, if I got that thing that's negative, I'm going to become negatively charged. You could call it an anion. These are just definitions. What is a positively charged ion? A cation. What is a negatively charged ion? An anion. What is an ion altogether? A charged particle. Yeah. Okay. So that's ionic bonds. Then there's the strongest bond. It's a covalent bond. A covalent bond involves sharing electrons. That is it. In an ionic bond, you share electrons. And electron share could vary. If you share 2 electrons, that's one pair. We call that a single covalent bond. If you share 2 pairs of electrons, which would be 4 electrons, we call that a double bond, etc. And we even give the symbols for it. A single dash represents a single bond where you're only sharing 2 electrons. A double dash represents a double bond, 4 electrons. That's it. You're just sharing electrons. But when it comes to sharing, you could share equally or unequally. So there are 2 subcategories for covalent bonds. You need to know these 2 subcategories. There's a nonpolar covalent bond, and there's a polar covalent bond. Keep it this simple. In a non-polar covalent bond, you equally share electrons. So there is no charges here. When you look at all the compounds or molecules that result, you don't see any negative or positive signs because there are no charges because everyone's sharing the electrons equally. On the other hand, you could share unequally. If you have unequal sharing of electrons, that's a polar covalent bond. And if you have unequal sharing, there's going to be an atom that's going to have more electrons because it's not sharing them equally. It will have more of those negatively charged electrons, so you will see a negative charge. While the other one that's not really getting the electrons as they're sharing, well, it's going to develop a slightly positive charge. You can always identify polar covalent bonds because you will see charges. All right. You'll see a negative charge closer to the atom or element that's pulling the electrons closer. And you'll see a slightly positive charge in the atoms or elements that are not getting the electrons. All right. That's it. No matter what you're sharing them. Sharing them equally, non-polar, there's no charges. Or sharing them unequally, polar, so there will be charges. It turns out water is an example of a polar covalent bond. Water will have a negative and positive end. Water is H2O. It's 2 hydrogens and 1 oxygen. Turns out oxygen pulls on the electrons harder than the hydrogens. So it pulls the electrons closer to itself and develops a negative charge, while the hydrogens have a slightly positive charge. And then there's the weakest bond. The weakest bond is hydrogen. What is this? It's an attraction based off opposite charges. That's what this bond is. You're not doing anything with electrons. You're not sharing them, you're not transferring them. This is just an attraction of opposite charges where one of the atoms is hydrogen. That's why it's called hydrogen. And this is actually how you get water to stick to other water. You can imagine if I had this water compound over here and this water compound over here, they will stick to each other because they will be attracted to their opposite charges. The positive charged hydrogens on one water compound will be attracted to the oxygen's negative charge of a different water compound. This is a type of hydrogen bond because at least one of the atoms is hydrogen. Okay, and it's an attraction of opposite charges. This is how you create something called water tension. Water tension or surface tension is the tension, the force on the surface of the water. Can you imagine if you've ever been to a pool, a lake, any large body of water, you might have seen insects walking on the surface of the water. They're walking on the surface of the water thanks to the surface tension, thanks to all the hydrogen bonds in that body of water. And these bonds are super weak. Why? Because you're not really holding on or transferring any pieces of yourself. You're just attracted to your charges. So these are super easy to break. You do it super easy. It's called drinking a sip of water. If you have a cup or a bottle of water, for you to take your sip, you need to rip that water away from the rest of water in the container. And that is super easy to do. It's super easy to take a sip of water because it's super easy to break hydrogen bonds. Why? Because they're the weakest of all. So know your bonds in order from strongest to weakest or weak to strongest, and know what's going on in each bond. Just rewind if you need to hear it again. Now that we know more about our atoms and elements and the bonds that hold them together, now we could go to work of doing chemical reactions. I could either make or break things down with chemical reactions. When we talk about chemical reactions, remember in anatomy, we name everything. Like in this chemical equation. A chemical equation is just a formula showing either how you make something or break it down. We name everything. Okay. When we talk about a chemical equation, it's kind of like a math equation where you're either breaking something down or building something up with addition. But instead of using an equal sign, we use arrows. Okay. So if you're to the left of the arrow, you're kind of like ingredients. So we call you reactants. If you're to the right of the arrow, you're like what we produce. You're the product. We just name everything in anatomy. And when it comes to either making or breaking things, when it comes to chemical reactions, you're either making or breaking bonds. And there's energy in bonds. So we got to spend some time talking about energy. What is energy? Good capacity to do work. It's not even you doing the work. I know I have energy because I know if I wanted to, I could get up from my table right now and walk away. I don't have to get up and walk away, but I know I have the capacity to walk away. I have energy. And even though it's a capacity to do work, we could still break it down. I know these two types of energy: potential energy and kinetic energy. Just no definitions. Potential energy is simply stored energy, while kinetic energy is the energy of motion. It's when you take your energy and put it to work. When I finally get up from the table, I'm using kinetic energy. So stored energy, potential, energy of motion or energy of work, kinetic energy. And yes, there are even further subcategories. I told you there's energy in bonds. That energy in bonds is called chemical energy because we're talking about chemicals. Or either when charged particles move, remember charged particles is an ion. When they move, that's a type of energy. It's called electrical energy. You might call it electricity. That's why when you get zapped by electricity, it hurts. You're literally getting hit by moved charged particles. When you're struck by lightning, you're struck by a ton of charged particles that are moving. And then the last type of energy that we talk about here is called mechanical energy. This is energy involved in kind of being transferred from one object to another. Kind of imagine if you're on your laptop, if you have a laptop and you're on it, your laptop screen is up. And when you're done, you're going to fold and close the laptop screen. When you're folding, you're moving that laptop screen. That's mechanical energy. Because normally that laptop would not close without any work on it. So you got to put in the work closing it. That is your mechanical energy. It's transferred from one object to another. As simply as moving something. Yeah. Know these two definitions. Remember, there's energy in bonds. So there's energy in chemical reactions. Some reactions, in order for you to go from your reactants to your products, you need energy. You require energy. You absorb energy. If you're a chemical reaction that needs, requires, or absorbs energy, you're an endergonic reaction. If, on the other hand, you give off energy or release energy as a chemical reaction, you're called an exergonic reaction. Know the difference. Know those two definitions. And then we actually talk about chemical reactions. You got to know these three basic chemical reactions and what's going on. There's a catabolic, sometimes called decomposition. Yes, they could use either name. There's an exchange, and there's an anabolic or synthesis reaction. Keep this simple. Catabolic reactions break large things down into smaller ones. If you call it a decomposition, kind of gives you a better hint. To decompose means to break down. This is when you break a large thing down into a small one. And in order for you to do that, you need to break a bond. And when you break bonds, that releases the energy trapped in the bond. So it turns out catabolic reactions, because when they break the bonds, that's up releasing energy, they're actually a type of exergonic reaction. Know that relationship. Know that catabolic reactions are exergonic. They release energy. Then there's an exchange reaction. This reaction tells you you're not breaking anything down overall. You're not bending up overall. You're exchanging one reactant for another, kind of swapping the pieces. That's what you see in this example. You have AB plus CD gives you ADBC. You just swapped the parts. You exchanged one part for another. That's an exchange reaction. So there's no overall give off of energy and there's no overall absorption of energy. You're just swapping the pieces. And when it comes to an exchange reaction, there's a subcategory for this. There's a specific type of exchange reaction. It's called an oxidation reduction reaction, sometimes called a redox. You just got to know definitions. What does it mean to be oxidized and what does it mean to be reduced? It has to deal with the electrons. If you lose electrons, we say you've been oxidized. If you gain electrons, we say you've been reduced. So think back to our ionic bond. Think back to sodium, where it gave its electron to chlorine. Well, in that case, sodium lost the electron because it gave it away. So sodium, in that example, would have been oxidized, while the chlorine gained the electron. So in that example, you could think chlorine was reduced. Keep it that simple. Lose electrons, oxidized. Gain electrons, reduced. And then there's your anabolic or synthesis reactions. To synthesize something means to build or make something. So that kind of gives you a hint. This is when you build a large compound or molecule from smaller reactants. You're building something up. Kind of think, taking individual bricks to build an overall brick house. That is an anabolic reaction. And to build this compound from smaller parts, you need to form bonds. And remember, bonds have energy. So if I want to form bonds, I need to put energy in. Anabolic reactions need or require or absorb energy. AKA, anabolic reactions are endergonic reactions. Know this relationship. Anabolic reactions are endergonic reactions. They also absorb energy. So know those three reactions. And then after you know those three reactions, then we got to know the things that could influence how fast the reaction could occur. Know these four factors that can have an impact on the rate or speed of your reaction. It's concentration of reactants, it's temperature, When they say property of reactants, they mean the size, big, small, medium, and phase, meaning solid, liquid, or gas, and whether or not something called a catalyst is present. These are the 4 factors. Then you need to know how is it going to affect the reaction. Is it going to make it faster or slower? So let's go through them one by one just to make sure. Just give you the answer straightforward. The higher the concentration, the faster the reaction will go. The lower the concentration, the slower will go. Then there's temperature. The higher the temperature, aka the hotter it is, the faster the reaction will go. The lower the temperature, or the colder it is, the slower the reaction will go. Kind of thing. If you've ever made tea, hot tea, and you put your sugar in, that sugar dissolves pretty quickly. Because that sugar dissolving in your water, that is a chemical reaction. It's a type of catabolic reaction, breaking down the sugar. And this happens fast because in hot tea. But if you ever made cold tea, iced tea, and tried to dissolve your sugar in it, it takes forever. And you're like, why? It's because of science. It's because of temperature of rates of reaction. And when you're trying to dissolve the sugar in the water, again, it's a chemical reaction. Now you're making iced tea, so the environment's cold. It's slowing down the reaction. That's why it takes so long. Oh, look at that, science. Okay. Keep going. What else could affect it? It's the size and phase of your reactants. I'll give you answers. The smaller the particles, the faster your reaction will go. The bigger, the slower. This principle applies to a lot of things in biology. Big things move slow, small things move fast. Kind of think a cheetah could run a lot faster than a big old elephant. Same thing for reactions. Smaller things will go faster than bigger things. So smaller reactants will have a faster reaction rate. Bigger reactants will have a slower reaction rate. And then the phase matter, solid, liquid, or a gas. If you're solid, that goes the slowest. Liquid goes a little faster. And a gas will have the fastest rate of reaction. And then lastly is whether or not something called catalyst is present. Just by having a catalyst present, your reaction will go fast. If it's absent, it will go slower. Why? It's because catalysts lower the activation energy. It kind of tells you that the activation energy is the energy you need to get started. And for some reactions, it's a lot of energy. So you're going to need time to build the energy up before you can start the reaction. That'll make it seem like it's going slow. But if I do have a catalyst, it lowers the amount of energy I need to get started. So I'm going to get started faster. I'm going to look like I happened faster. When the catalyst is absent, slow reaction. When it's present, fast reaction. And it turns out a lot of enzymes in your body are catalysts. There are enzymes, aka proteins, that can speed up a reaction by lowering the activation energy. So those are things that can affect the rates of your reactions. And that's all the basic chemistry in this chapter. The rest of this chapter switches over to biochemistry. Now we're taking regular old chemistry and applying it to our lives, our body. And with that, we're really looking at compounds in the body. We look at inorganic and organic compounds. As we go through this last section, it's pretty straightforward. We're going to look at inorganic stuff first and organic stuff. And what's the difference? What's it mean to be organic or inorganic? What I see when I look at your molecular formula, what you're made up of, what atoms and elements are making you up. If you have carbon bound to hydrogen, you're organic. You might have heard the phrase, if you're made up of carbon, you're organic. That's not the full definition. To be organic means yes, you have carbon, but that carbon needs to be bound to hydrogen. If you do not have carbon bound to hydrogen, you're inorganic. So just plain old carbon's not good enough. Why? What's an example? An example is carbon dioxide. That's CO2. That's 1 carbon and 2 oxygen. That's the gas you breathe out. That's inorganic. Why? Because yes, it has carbon, but it's CO2. There's no hydrogens anywhere. So it's not organic. The air you breathe out is actually inorganic. So we're going to look at some inorganic compounds like water, acids, and bases. Then we're going to look at some organic ones. Starting off with water. Water is inorganic. How do you know? Because when you look at the formula, it's H2O. There are no carbons anywhere. So it's definitely inorganic. All you got to know are some features of water. And just know some characteristics of water. For one, it makes up the majority of your body. Up to 80% of your body's mass is just water. And that's for a good reason. Because of these key properties. You got to know these key properties, these characteristics of water. For one, water has a high heat capacity, meaning it could absorb a lot of heat before it begins to change. Think boiling. This is why it takes so long, or it feels like it takes forever to boil water, because you need to allow the water to absorb enough heat before it begins to change. And because it has a high heat capacity, it means it could absorb a lot of heat before it will begin to change. That's why it takes so long to boil water, because water has a heat capacity. And this is good for us, because mainly water. Why is this good? Well, sometimes you get hot. It's called a fever. It would be really weird if every time you got a fever, you saw your skin, little water in your body bubbling under your skin. Ew, that would be weird. But luckily, it doesn't happen because water has a high heat capacity. It can absorb all that heat as we're having our fever, our high temperature. Keep going. Another feature of water is that it carries heat with it when it evaporates. This is good for us because, again, we get hot. Whenever we get hot, one way we cool down is by sweating. Just by sweating alone, that's not what cools you off. You sweat in order for evaporation to occur, so that when evaporation occurs, it carries heat with it and you will cool down. So if you're ever outside and someone has a heat stroke, yes, throw water on them, but you're not done yet. You got to fan them to allow the water to evaporate off their skin, and it could carry the heat with it and they will cool down. Keep going. Water can even act as a cushion. Think a pillow, like a water balloon. You have some areas of your body that have water in it to provide cushion. And we've already seen water could be a lubricant. Remember, we saw serous fluid separating the parietal and visceral layers of the serous membrane. That serous fluid is mainly water. Why? Because water is a good lubricant. It can reduce friction. Know these features. I'll just ask, what are these characteristics? It has high heat capacity, it carries heat when it evaporates, it acts as a cushion, as a lubricant, to produce friction. What else? We saw that water is also a solvent. It dissolves solutes. That's why you produce saliva when you're eating. That saliva, as soon as you put food in your mouth, is helping you to break stuff down because it's dissolving. Because water is a powerful solvent. So, and then again, some definitions. You gotta know what it means to be hydrophilic and hydrophobic. It deals with water. It tells you the name. Remember, don't be intimidated by any names in this class. Just break them down. Hydro means water. Philic means loving. So when you're hydrophilic, it means you love water. Technically, it means you like to dissolve in water. Okay. Salt is hydrophilic because salt will dissolve in water. All right. But some things don't like water. Call them hydrophobic. And hydro means water, phobic as in phobia. It means water fearing. But technically, it means you do not dissolve in water. So do you dissolve in water? Hydrophilic. Do you not dissolve in water? Hydrophobic. Why? It has the charges. Water could dissolve things, but it's a polar covalent bond substance, meaning it has charges on it. Remember, our oxygen has a slightly negative charge and the hydrogens have a slightly positive charge. So when they dissolve things, they're just really pulling on them based off the charges. When you drop salt in water, salt dissolves because the negatively charged chlorines, because you remember it got the electron, so it has a slightly negative charge, it will be attracted to all the positively charged hydrogens. While that sodium, remember, it gave away an electron, so it got oxidized and became slightly positive. It will be attracted to all the negative charges on the oxygens. That's how it's ripping the salt apart and getting it to dissolve. If you have a charge, you're likely to be dissolved by water and you'll be considered hydrophilic. If you do not have charges, how do you not have a charge? Remember, that's the result of a non-polar covalent bond. Well, the water can't pull you apart. Things like oils and fats are the results of non-polar covalent bonds, so they are not charged, so they will not dissolve in water and are considered hydrophobic. So that's water, and know those definitions. Then we look at acids and bases. These these are also inorganic because when you look at their formulas and what it means to be an acid and a base, you will not see carbon bound to hydrogen. So it's inorganic. You got to know, what does it mean to be acid and what does it mean to be base? Keep it this simple. An acid, when you drop it in water, will break apart and release positively charged hydrogen ions. That's what it means to be an acid. When you dropped in water, it will break apart. We say you dissociate, it means break apart. And you will release positively charged hydrogen ions. That is an acid. While a base, when you drop a base in water, it will also break apart and release negatively charged hydroxyl or hydroxide ions. That is it. That's the definition. Acids, when you're dropped in water, you release positively charged hydrogen ions. But what does that mean? Well, a positively charged hydrogen ion is really just a proton. Remember, normally hydrogen has an atomic number of 1 and a mass number of 1. So there are no neutrons. Only one proton, and if it's neutral, stable, it also has 1 electron. But for you to be a positively charged hydrogen ion, positively charged because you lost that 1 electron. So when we say a positively charged hydrogen ion, this thing here, we're really saying it's a proton because that's all that's there. So when you're dropping acid in water, it releases these positively charged hydrogen ions. It releases protons. So we sometimes call an acid a proton donator. While a base, sometimes called an alkaline substance or alkali substance, it releases those negatively charged hydroxide ions. Those negatively charged hydroxide ions love to bind to positively charged hydrogen ions. Why? What do you get when you combine 1 oxygen with 2 hydrogens? You get water. So, and you know these positively charged hydrogen ions are really a proton. And since you love to bind protons as a base, we sometimes call them proton acceptors or hydrogen ion acceptors. So that no acids release positively charged hydrogen ions in water, and bases release negatively charged hydroxyl ions in water. And then you got to know the pH scale. Where on the pH scale is considered an acid, and where on the pH scale are you considered a base? Well, your pH scale is a simple scale, goes from 0 to 14. If you are less than 7, you are considered an acid. So that means a pH of 0 to 6.99, that is an acid. And a base is greater than 7. So as soon as you're above 7, 7.01 all the way up to 14 is a base or an alkaline substance. So if you drink alkaline water, well, you're not drinking anything fancy. You're just drinking water that's a little basic, had some base added to it. Okay. And notice I jumped all around 7. You're either above 7 or less than 7. What happens at a pH of 7? At a pH of 7, you're considered neutral, meaning the number of hydrogen ions is equal to the number of hydroxide ions. And you remember, what do you get when you combine that hydrogen with hydroxide? You get water. So water has a pH 7, neutral. You like to test this. They'll say you have this with pH of 6. Is that an acid or a base? It's an acid. They could ask this question. Which of the following substances is the strongest acid? Is it a substance with a pH of 5, a pH of 3, or pH of 1? Which is the strongest acid? pH of 5, pH of 3, or pH of 1? It's a pH of 1. The more extreme you are, the stronger you are. Same for base. Something with a pH of 14 is stronger base than something with a pH of 8. The more to the ends of our scale you are, excuse me, the stronger you are. Closer to neutral you are, the weaker, as both an acid or a base. And then they could ask one more way. You got to remember what they release. Remember, bases release negatively charged hydroxide ions, and acids release positively charged hydrogen ions. So I could ask a question like this. Which of the following substances has the highest concentration of hydrogen ions? Is it a pH of 13, a pH of 7, or a pH of 2? Well, it's pH of 2. Because if you have a lot of positively charged hydrogen ions, well, you must be an acid. All right. So that's based off the concentrations of hydrogen ions or hydroxide ions. And just remember, acids release hydrogen ions, and bases release hydroxide ions. And you have to know what is a buffer. By definition, buffers are chemicals that resist large changes or large swings in pH. How so? If you were to test your blood's pH, your body's pH, you're close to neutral. Remember, you're mainly water, so it makes sense you have a pH close to neutral. But we put things in our body that are sometimes acidic or sometimes basic. For example, you might like lemonade. All right. Turns out lemonade is made of lemon juice, which is extremely acidic, close to a pH of 2. All right. But if I drink some lemonade and you check my pH, I'm not going to drop to 2. I'll still be in my neutral zone. Why? Because I have buffers resisting that change. It's preventing me from becoming too acidic or too basic. That's the job of a buffer. So you have buffers in your body to help keep you close to neutral, help resist large changes in pH. All right. And then the last inorganic substance is a salt. All right. You already know all about salts. Salts are the result of a metal transferring an electron to a non-metal, forming an ionic bond. You already knew that. And we already know salts are solutes. Why? Because salts dissolve in water. And when they dissolve in water, we already know it's because the water was ripping them apart based off their charges. So we already know about salts. And that's all our inorganic compounds. Then to finish off this chapter, we look at our organic compounds. It's a lot of them. We're going to look at carbohydrates, lipids, proteins, and nucleic acids. These are all examples of organic compounds. So when we look at all their formulas, we will see carbons bound to hydrogen. But what do you need to know? We're going to keep it simple. For all these organic compounds, carbohydrates, lipids, proteins, and nucleic acids, you need to know what are the monomers. A monomer is a building block. It's an individual subunit. Kind of think in a big brick house, an individual brick is a monomer. And you got to know the polymer. It's the big compounds you're going to form. Again, imagine your big brick house. If the brick is the monomer, the entire brick house is the polymer. Monomers are building blocks to build up the polymers. So for each of these groups, carbohydrates, lipids, proteins, and nucleic acids, you need to know what is a monomer and what is the example. What is an example of a polymer? And how do you make the polymer and how do you break them down? It's going to be a chemical reaction. And it's going to be the same 2 chemical reactions for all of them. It's the same chemical reaction that builds up carbohydrates, lipids, proteins, and nucleic acids. It's going to be the same chemical reaction that will break them all down. It's these 2. To build them all up, remember, to build something is a synthesis or an anabolic reaction. In this case, it's specifically a dehydration synthesis reaction. That's how you're going to build all of them. And a dehydration synthesis reaction is just building something by removing water. And to break them down, you just throw water to break. When you use water to break bonds, to break something down, that's a hydrolysis reaction. Hydro means water, lysis means to break. So it's when water breaks bonds. That's to break them all down. That's why and you have spit in your saliva. You're using it to break bonds, to break things down. So you already know first 2 things, or at least 2 of the 4 things you need to know. What's the monomers? What's the polymers? How do you make them? How do you break them down? You make them all by removing water, dehydration synthesis. You break them all down by using water to break bonds, hydrolysis. So for the rest of this, just going to quickly go through them and pinpoint what is the monomer and what is the polymer for each of them. Why? Because you're all going to be made with dehydration synthesis, and they're all going to be broken down with hydrolysis. So first up are carbohydrates. What's the monomer? What's the building block for your carbs? It's sugars. It's a single sugar. We call that a monosaccharide. Mono 1, saccharide means sugar. So the monomer for carbs are monosaccharides. And you need to know an example of a major monosaccharide in our body. It's glucose. Glucose is the major monosaccharide for your carbohydrates. And then you gotta know what's the polymer. Well, if the monomer is one sugar, mainly glucose, polymers can be many sugars. It's called polysaccharides. Poly means many, saccharides means sugars. And again, you gotta know an example of the major polysaccharide in your body. It's glycogen. Glycogen is the major polysaccharide in your body as a human. That's all you gotta know. Carbohydrates are organic compounds. Monomers are called monosaccharides, where an example is glucose. Polymers are called polysaccharides, an example glycogen. You build it with dehydration synthesis, and you break it down with hydrolysis. That's it. You don't have to identify anything. I'm not going to show you pictures and ask which one's glucose, or I'm not going to ask what's the picture of glycogen. I'm not going to ask a picture of dehydration synthesis. Don't need to know pictures. Okay. But that's it. That's carbohydrates. Then we do the same thing with lipids. What's the building block? The building block for lipids are fatty acids. Fats are an example of a lipid. Oils are an example of a lipid. The monomer is the fatty acid. That's it. Fatty acids are the monomers. But when it comes to fatty acids, you have two major groups of them. You got to know the two major groups of fatty acids and what they look like. There's a saturated fatty acid, and there's an unsaturated fatty acid. It has to deal with how the carbons bind to hydrogen. If all the carbons in the fatty acid have maximized the number of hydrogens they could bind to, it's like they have covered themselves with hydrogen. They have saturated themselves with hydrogen. You have a saturated fat. Saturated fatty acids are just fatty acids where the carbons have bound to the maximum number of hydrogens possible. If you do not bind to the maximum number of hydrogens, well, then you're an unsaturated fat. How would I tell? Just by looking, this is an unsaturated fat. Boom, right here. These, you see, most of the hydrogen, or most of the carbons in this picture have bound to at least two hydrogens, except for these two. Instead of binding to a second hydrogen, they chose to double bond to each other. When you see double bonds in a fatty acids formula, you are looking at unsaturated fatty acid. Those carbons have not maximized the number of hydrogens they could bind to. Okay. So those are the monomers. It's fatty acids, either saturated or unsaturated. And then you'll have your polymers. Gotta know an example. It's a triglyceride. Triglyceride is a major polymer lipid in your body. It's the major fat in your body. And because of that, you got to know what it looks like. Got to know what are the parts to triglyceride down here. Triglyceride is made up of one glycerol molecule and three fatty acids. It's all in the name. It's called tri, because it's made up of three fatty acids, and glyceride, because it's also made up of one glycerol molecule. That's it. So for your lipids, again, monomers are fatty acids, either saturated or unsaturated. The polymers triglyceride made up of glycerol and three fatty acids, and you make it with dehydrated synthesis, and you break it down with hydrolysis. And yes, there are other fats in your body, but we'll see them later in the semester. Like phospholipids, you'll see next chapter helping to form the plasma membrane. Those are in the name. They are a type of lipid. They're a type of fat. Other fats too, like steroids. Yes, the steroids athletes might take to get bigger, stronger, faster. They're actually injecting themselves with a modified type of fat. Yeah. But anywho, keep going. Remember, this is just a review. Then there's proteins. Again, what's the monomer? What's a polymer? You already know how to make it. Dehydration synthesis and break it down. Hydrolysis. So what's the monomer? The monomers are called amino acids. Amino acids. They're the building blocks of your proteins. And there are over 20 of them. No, you do not need to know the names of any of the specific amino acids. Just know that amino acid is the monomer. And to make a protein, you just got to stick amino acids together. But there's a special bond here. You got to know the bond between amino acids called a peptide bond. It's specifically a bond between the carbon of one amino acid and the nitrogen of the next amino acid. It's a peptide bond. It's the bond between the carbon of one amino acid and the nitrogen of another amino acid. And so the polymer is called polypeptide because it's really made up of many amino acids held together by many peptide bonds. So the polymer is called polypeptide. There's no specific names like there were with carbohydrates. And that's it. Proteins, monomer, amino acids. Polymer, polypeptides. What's holding the amino acids together? Peptide bonds between the carbon of one amino acid and the nitrogen of another. How do you make it? Dehydration synthesis. How do you break it down? Hydrolysis. Sorry. But again, proteins are still a little complicated. It's not like carbohydrates or lipids. Why? Oh, with carbohydrates, as soon as you add together your sugars, you have your carbohydrate. When you're doing your fats, as soon as you add your fatty acids together, you have your fat, your lipid. But with proteins, once you add your amino acids together, you're not done yet. Your protein is not ready to work. You need to change the way it looks. You need to alter its structure before it becomes functional. So we gotta go into the structural levels of a protein. I want you to know your 4 structural levels of your protein in order. And the order is primary, secondary, tertiary, quaternary. Tells you in the name, it goes in order. And you got to know what protein looks at each of these levels. What does a protein look like at the structural, secondary, tertiary, and quaternary level? And at which of these levels is your protein functional? At which of these levels does your protein finally work? I'll answer that one right now. Your protein is functional at the last level, the quaternary level. So you got to do all this altering all to get it to the quaternary level, which is the level where your protein will finally work. What do they look like? It's all on this little slide here. Your primary level is just a linear sequence of amino acids, a string of amino acids, kind of like pearls on a string, all held together by peptide bonds. Your secondary level, what you do to the primary. If you take your primary level and bend it, fold it into what we call a beta-pleated sheath, or twirl it like ribbon into an alpha helix, that is your secondary level. So you altering the primary level, either by bending it into beta-pleated sheets or twirling it into an alpha helix. When you combine multiple secondary levels together, that is your tertiary. That's what you see here. This big glob, if you kind of zoom in, you see a fold, you see beta-pleated sheets, I see a ribbon, I see an alpha helix. I see multiple secondary levels combined together. That is the tertiary level. And then your quaternary level is also simple. It's multiple tertiary levels brought together. This one overall tertiary level has what we call globular shape. It looks like a big glob. And here's a fibrous protein. It looks like a fiber, like a string. If I had multiple tertiary levels together, that is the quaternary level. It is at that level the protein is functional. Know your levels. And then the last organic compound are your nucleic acids. This is really your genetic material, your DNA and RNA. Your DNA and RNA are organic compounds. They literally have formulas that will show carbons bound to hydrogens. But again, what do we care about? What's the monomer? What's the polymer? You already know how to make it, dehydration synthesis. You already know how to break it down, hydrolysis. So what are the building blocks for DNA and RNA? What are the monomers for your nucleic acids? They're called nucleotides. Nucleotides are the monomers for nucleic acids. And even though it's a building block, even though it's the monomer, itself can be kind of broken down. I want you to know the 3 parts to a nucleotide. So here, all nucleotides will have a nitrogenous base. That's just a base that will have nitrogen in its formula. It will have a nitrogenous base. It will have a sugar, and it will have a phosphate group. That's what you see on this picture. It will have a base, it will have a sugar, and it will have a phosphate group. Just know that. Know the 3 parts to a nucleotide. Remember, this class is mainly memorization. Then you got to know differences between DNA and RNA. They are both organic compounds. They are both made up of nucleotides. So what's different? Well, it's really the parts to the nucleotide. Turns out there are different bases in the nucleotides. They're what we call purines, pyrimides. Once you know the specific bases, there's adenine, guanine, cytosine, thymine, and uracil. These are your 5 major nitrogenous bases. You got to know which ones are found in DNA and which ones are found in RNA. First is DNA. DNA has adenine, guanine, cytosine, and thymine. Those 4 can be found in DNA. RNA has similar ones. It has adenine, guanine, and cytosine. But there is no thymine in RNA. Instead of thymine, it has uracil. So that's a major difference between DNA and RNA. What bases do you have? They both have adenine, guanine, and cytosine, while DNA has thymine and RNA also has uracil. And then this also relates to energy in our body. Why? Turns out our energy in our body, in our cells, is really a nucleotide, a modified nucleotide called ATP. ATP stands for adenosine triphosphate. It's really a nucleotide with 2 additional phosphate groups. It's called triphosphate because it has 3 instead of 1. But it's still a nucleotide. It tells you the name. It's called adenosine because it has an adenine nitrogenous base. It has a sugar, ribose sugar, and it has 3 phosphate groups instead of 1. ATP is technically a nucleotide. But this is the energy form for your cell. The energy is in the bonds. Remember, this is chemistry, so this is chemical energy. Energy in bonds. Turns out when you store energy, you'll take a lesser form of ATP called ADP, adenosine diphosphate. Di means 2, so it only has 2 phosphate groups. And you will give a phosphate group to it and form a bond. Trap all the energy in that bond. The one bond between the 2nd and 3rd phosphate groups have the most energy in this compound. So let's say you ate breakfast and then you want to go take a nap. Odds are, if you ate breakfast and then took a nap, you probably ate more energy's worth of food than you need. So your body's going to store some by taking ADP, giving that extra phosphate group, forming the bond and storing the energy. Then let's say later in the day, you go to the gym. Now you need energy to power your workout. Your body's going to go in the opposite direction. It's going to take ATP and pop off that 3rd phosphate group. When it pops it off, it breaks the bond and releases the energy. This is why your body loves ATP as the energy source. It's super easy to add on or pop off that 3rd phosphate group. But at its core, it's really just a special type of nucleotide. So you technically could use it to help make DNA and RNA. But again, what are some more differences? Go back to the nucleotides. Remember, it's made up of bases. We know the differences in the bases between DNA and RNA. So there's DNA uses deoxyribose as its sugar, while RNA uses ribose. And they actually tell you the name. DNA stands for deoxyribonucleic acid. It's telling you the sugar that it uses. RNA is called ribonucleic acid. For ribose, it's telling you the sugar in the name. All right, keep going. Then another difference is what they're doing. What does DNA do and what does RNA do? Turns out DNA is like a big recipe book. It's a master blueprint on how to make you. Anything in you, mainly it's like your protein. Think DNA as a big recipe book telling you how to make all the proteins in your body. But let's say you want to make just one protein. Well, it's like you just need one recipe. We call that a gene. A gene is a part of your DNA that tells you how to make one protein. When we say code for something, it's like saying you give instructions or a recipe for something. So a gene is just a part of your DNA that codes for or tells you how to make a specific protein. That's what DNA does. While RNA is really not telling you how to make all the proteins. RNA really helps with only minor details. But DNA could tell you how to make everything. And when you look at DNA, we see it has a double helix arrangement. It's made up of two strings of nucleotides bound together, and it twirls or twists. So we call it a double helix. Where if you were to look at RNA, you'll just see a single strand. The RNA is single-stranded. It's only made up of one string of nucleotides. So just talking about some differences between DNA and RNA. Make sure you know these differences. These slides are just repeating what I said. DNA has deoxyribose as a sugar, has bases adenine, guanine, cytosine, and thymine, has a double helix arrangement. And what's holding this double helix together? It's really the nucleotides. It's really the bonds between the bases of the nucleotides. So we got to know how the bases come together. And we know how. We know specifically adenine will bind to thymine and vice versa. Thymine will bind to adenine. And guanine will bind to cytosine. Or cytosine will bind to guanine. Know that. Adenine to thymine and DNA and cytosine to guanine. That's what you see. This guanine here is binding to this cytosine. This adenine is binding to this thymine. That's how you're holding those double helix strands together. Now, RNA, remember, it does not have thymine. Instead of thymine, it has uracil. So when we talk about how bases come together, instead of having adenine bind to thymine, because there's no thymine, it will bind to uracil. All right, guanine will still bind to cytosine. And again, RNA helps tell you how to make a single protein. It doesn't tell you how to make all your proteins. And really, you get RNA from DNA. So if I need to make a protein, we will start off with DNA first. And then I would have to make the middleman called RNA. And then I would use the RNA to make the protein. So if we talk about protein synthesis, making proteins, you got to do two things. You got to know these two definitions. There's something called transcription, something called translation. Transcription is the process of making RNA copy of DNA, basically making RNA from DNA. While translation is you making your protein from RNA. So it's just really a two process. Turn or make a copy of DNA called RNA, transcription, or make your protein from RNA, translation. All right, so that's a little bit on your nucleic acids, and that's chapter 2.